So we've seen that the speed of light is really a very fundamental limit. This, to me, is really annoying. I'm a great science fiction fan, and it's always a real pain, the stupid law of physics that says you can't go faster than the speed of light. Just imagine Star Wars. So let's go to Alderaan. Okay, 200 years later you arrive. It makes a very unexciting story. And when I was a kid, it used to try to think about ways around this. One idea a lot of people have about beating the speed of light limit is that in the course of the history of science there had been many limits to speed. Back in when the first railways were coming along the line, people thought, you can't go more than 30 kilometres an hour, the stress will shake people to pieces. And of course that's long since been passed. Then much more recently there was a speed of sound limit. Aircraft can't penetrate the sound barrier, and then they penetrated it very shortly afterwards. So is the speed of light a barrier like that that's just waiting for some future technology to break it? I mean, what would happen if you build a really powerful rocket and you go up to 99% of the speed of light, then you put your foot down on the accelerator? Wouldn't you just cruise past the speed of light?
Unfortunately, it seems, as near as we can tell, with our understanding of special relativity, that it really is a hard limit, because light is always going the same speed no matter what you're doing. So no matter what you do, you're going 99% of the speed of light, light leaves you at the speed of light. You want to press the accelerator down, you want to go 99.9% of the speed of light. Well, you don't go over 100% because you always have the speed of light going at the speed of light away from you. And the way this is all compensated for is because time ends up being dependent on your reference frame.
So your own frame of reference, so let's say I'm accelerating, and I accelerate. Or let's say I start off at rest. I shine a beam of light forward, it's going away at 300,000 kilometers a second. Then I accelerate, use my antimatter drive and whatever, and when I shine the light forward, it's still going at the same speed. And no matter how fast I go, shine the light out, it goes at exactly the same speed. I can't catch up.
That's right. You can't violate it, but it does have some interesting, I would say, science fiction-like effects. So imagine I start heading towards Alpha Centauri at 4.3 light years. Now, if I shoot a photon off, it's going to take 4.3 years to get there. Unless I'm actually on a rocket ship, because of that time dilation. When I'm heading towards Alpha Centauri and I go faster and faster, Alpha Centauri looks closer and closer to me, and the amount of time it takes for me to get there ends up being very short. It ends up being, if I go fast enough, a few seconds within my frame of reference to get there. So I can get to Alpha Centauri in a few seconds.
Which sounds like you're breaking the speed of light limit, but not really from your frame of reference. Going at 99.9% of the speed of light, light is still going at c faster than you. The reason why it takes such a short time to get there is because Alpha Centauri is no longer 4 light years away, but it's actually only a few meters away.
That's
because
right.
It's the length's contraction. But if you're flying past and I'm looking at you, from my point of view, it's not Alpha Centauri is still 4 light years away because I'm stationary. What's different is that your time seems to have slowed down. But to you, the time doesn't seem to slow down. For you, my time seems to slow down.
Right. So we could imagine doing an experiment, which I would love to be able to do, is I build a rocket ship. I head out right now at almost the speed of light to Alpha Centauri. I go visit it, and I come back a few seconds later, and I'm going to tell you all about it.
Yeah, at the moment we're about the same age, but when we came back, I'd now be 8 years older than you.
That's right. And I would be confused because it only took a few seconds. Hey, what were you doing getting old? And this seems crazy, but there are ways that we can actually test it in the lab.
Yes, you can routinely get a particle, some atomic particle that, for example, would only normally last a millisecond left to itself, and you bring it up to 99.9% of the speed of light, and it can last for hours or weeks. So this is something that's not just a purely theoretical thing. We can test this and do test it all the time in our labs. For example, there are natural particles, muons, hit the upper atmosphere, and normally they wouldn't penetrate the atmosphere, but because they're going so close to the speed of light, their clock slows down from our frame of reference, so they can penetrate the speed of light. From their own frame of reference, time is going normal, but the atmosphere is much shortened.
Yeah, it's just a small little bit. And they've even done it more directly, I think, for people's senses. They've went and taken these atomic clocks, which keep, very precise time. And you would have 2 of them. You put one of them in an airplane and the other one not. And then they come back and they see that, indeed, the clocks have become disentangled, essentially, is that they're no longer on the same time due to this exact effect. So it's real. It's crazy.
But it is real.
But it is the universe we seem to live in.
And going back to this accelerating faster than light business, I mean, if I'm trying to accelerate, no matter how fast I accelerate, the speed of light is always going faster than me. It's a bit like most skills in the real world. No matter how good you get at something, you realise there are people who are better than you at whatever you want to do. So it's not so much that I can't go faster than light, it's no matter how fast I go, light's still going to see faster. But if you're looking at me, what would I seem like?
Well, if I'm looking at you trying to go fast, well, then you end up looking very, very squashed to me because of this distortion, this contraction. You end up looking almost like a sheet of paper moving off into the distance. So you look very funny.
And my time slows down, and also my mass appears to go up. So when I'm at 99.9% of the speed of light and I put my foot on the accelerator, my mass is now maybe thousands of tons.
And that means you're going to need a lot of energy to do it.
Yeah.
Because that energy to get going faster and faster becomes enormous, and getting the last few nines, the amount of energy could end up being the entire energy of the universe to go that fast.
So from someone else's point of reference, what stops you getting faster the speed of light is as you get closer to the speed of light, your time slows down, also your mass goes up. So you need an infinite amount of energy to add another 0.9 or another 0.99 to it. And so without all the energy of the universe and then some, you can never actually penetrate the speed of light.
That's right. So this is not just a hard limit to pass, it probably is a hard limit to pass.
A very fundamental limit.
Yeah.
Anyway, now I'd like to talk about, take this back to black holes. And to do this, we're going to have to introduce a new form of diagram, one that combines both space and time. So let's talk about that.